Welcome to our tutorial on the 8085 16-bit arithmetic and compare instructions. Okay, so here we're gonna start with the 16-bit arithmetic instructions. Okay, and in that category we begin with the increment and decrement instructions first. So over here we got two instructions, that is the INX and the DCX. Okay, and both of whose operands are the specified register pairs. Okay, now if we just start with the INX instruction first. So here INX instruction stands for increment the 16-bit data that the specified register pair contains by 1. So if you just execute the INX instruction once, then the 16-bit data content in the specified register pair would just be incremented by 1. Okay, and similarly the DCX instruction that we got over here just does the opposite, that it just decreases the 16-bit data contained in the specified register pair by 1. Okay, so let's have an example over here. Let's say we have got the BC register pair. Okay, and let me just tell you that all the register pairs that are possible out of the general purpose register, registers that are present in the RAM of the inbuilt RAM of the 8085, and even the stack pointer register also comes it can be taken as the operand for these two corresponding instructions. Okay, and it's worth mentioning that both of these instructions are just single byte. Okay, and now just let's go on to our example. Let's say the let's just take the BC register pair. Okay, so let's say the BC register pair. Okay, so let's just data byte be taken as, or rather the 16-bit data be taken as well. Let's just take it this way: A251H. Okay, so all right, we can just do with that. Fine. So if this is the actual 16-bit data in the BC register pair, okay, and now we use this INX statement. Okay, so we just write it this way: INX, and just write here B. Okay, now if we write INX B, then B actually means, or rather stands for, the BC register pair. Okay, so what happens is that after this instruction will get executed, okay, by the 8085 microprocessor, then the data content in the BC register pair would increment by 1. So now the new data, okay, new 16-bit data in the BC register pair is A252. Okay, and earlier it was just A251. Okay, so now you can just understand the difference over here. Okay, so now similarly, as I just told you a little while ago, that whenever we're working with the BC register pair, we're supposed to write here INX and then give B. Okay, if we're working with the DE register pair over here, okay, if we were working with the DE register pair, okay, and let's say if the data byte was 00 A E, okay, and if we wanted to increment this thing, okay, we would have written the instruction somewhat this way: INX D. So if we write here D, then it would mean, the 8085 would understand that we're talking about the DE register pair, and then the data in the DE register pair would get incremented to 00 AF. Okay, so this would be the new data, 16-bit data in the DE register pair. All right, so that's how this works out. So whenever we're now, you should also realize this thing, that whenever we're working with a 16-bit data, let's say for example, let's just take this data over here, 00 AF. So here the first two digits, okay, that just represents the higher byte. Okay, there you go, that's the higher byte, and the last two over here represents the lower byte. So whenever we are working with the INX or the DCX statement, we shall also see that the same thing is applicable for the DCX statement as command as well. Okay, so whenever we are working with these instructions, we are supposed to specify the name of the register that actually contains the higher byte of the 16-bit data, contained in the corresponding register pair. Like for example, if we're talking about the BC register pair, then it's obvious that the register B contains the higher byte. Okay, so this higher byte, that is A2, is present in the register B, so we write here INX-B. Similarly, in the other example, the register D of the DE register pair actually contains the higher byte, that is 00. Okay, and that's why we write INX-D. Okay, and similarly, if we'd work with the HL register pair, we would write INX-H. Okay, and now, as I said, well, the DCX command does the exact opposite of what the INX does. So it just decrements the data. So let's just take the one of the previous examples. Let's say the BC register pair right now contains the 16-bit data A252H. Okay, and now if we would write here DCXB, then after this instruction gets executed, then the data, 16-bit data in the BC register pair, decreases by 1 to A251 like it was before. Okay, so whenever we would execute this particular statement, it would just decrement the 16-bit data just by 1. And the way in which this is declared, the DCX is declared, is just similar to the INX statement. We always give the name of the register, okay, that contains the higher byte of the this is just the register containing the higher byte in the register pair with which we are just working. Okay, now since we're working with the BC register pair over here, and that the register B contains the higher byte of the 16-bit data, okay, contained in the BC register, so we just write the name of the B register that just contains the higher byte. Okay, similarly, if we'd work with other registers, okay, as I just showed you over here, you would do the same. Okay, let's give another another example over here. Let's say if the DE register pair would contain this particular data, like for example 00AF, okay, and we would need to decrease it, then we would write here DCXD. Now this instruction obviously refers to the DE register pair, so we specify the name of the register, okay, in the DE register pair, that is register D, that contains the higher byte of the entire 16-bit data. So this gets decreased to, well, let me just make the box over here, 00AE after this instruction gets executed. So that's pretty simple over here. Okay, and now let's just move on to, oh, and I just almost forgot that, well, the flag bits, okay, for these two instructions are completely unaffected. So these instructions do not affect any of the flag bits. Okay, so now it's finally time to move on to another one of the very important arithmetic instructions. Now here we have the 16-bit addition instruction, okay, known as DAD. Okay, sounds kind of weird, I know, but well, I just referred that way. Now this instruction actually means that add 16-bit data in the specified register pair, which is just its operand. Okay, you can see over here. So the 16-bit data that is basically is present in the specified register pair, okay, that's the operand of this instruction, to the 16-bit data that is contained in the HL register pair. Okay, so let's just highlight this by an example. Let's say the register let's say the register DE, okay, register pair DE to be more precise, which contains the data byte of, let's say, what can it be, okay, 02A0. Okay, so this is the 16-bit data present in the DE register pair, okay, and let's say the HL register pair on the other hand what contains the data, a 16-bit data, okay, of let's say what could it be, okay, A052. all right, so we are supposed to, now if we basically want to actually, well, add these two 16-bit data up, okay, then what would you do? We would basically use this instruction that's known as DAD. Okay, now if we'd write here DAD and then specify the name of the specified register pair, okay, whose 16-bit data we want to add with the 16-bit data present in the HL register pair. So there is the DE register pair which has 16-bit data over here, so we write here DAD D. So notice this way of declaration of this instruction. You always give the name of the particular register in the register pair that just contains the higher byte. Okay, similar way in which we declare the instructions in the case of the INX and the DCX instructions. Okay, so over here what we can see is that if we just write here DAD D, okay, give the instruction this way, and once this instruction gets executed by the 8085, the content of the HL register pair would just change, and this 16-bit data now contained in the HL register pair would just be the result of the addition between the data 16-bit data in the DE register pair and the one that was previously present in the HL register pair. Also, I mean, that was A052 actually. So this was the previous data content. Okay, so this is actually the previous 16-bit data. Okay, 16-bit data in HL register pair. Alright, so in HL. Okay, and this was the data by 16-bit data in the register DE, and after these two, I mean this instruction gets executed by the 8085, the 16-bit result, okay, of the addition of these two 16-bit numbers also gets stored in the HL register pairs itself. Okay, so that's what this instruction DAD does. Now this instruction is just a single byte instruction, as you can see, and as for the as for the flag bits, okay, this instruction only affects the carry flag, okay, and doesn't affect the other flags at all. Okay, and the carry flag is affected, I mean the carry flag is basically set only if this result is larger than 16 bits. But in this example, as it says, in this example, since the result is 16 bits only, it's not larger than that, so the carry flag is 0 because we don't have any carry. So this addition doesn't produce any kind of carry bit, so no carry in this case, and that's why the carry flag remains set to logic 0 level. Okay, and now we just finally arrive at the data compare instructions. Okay, now we got two instructions in this category, that's the CPI and the CMP. Okay, now CPI actually refers to this instruction has an 8-bit data as its operand, as you can see over here, and what this instruction actually implies is that it says compare immediately the specified 8-bit data acting as the operand here, okay, with the data byte that is present in the accumulator register. Alright, while the CMP, this instruction has a specified register or a certain memory location, okay, as its operand. Now you don't write any memory location over here, so this actually represents the memory that I'm just talking about here is just represented with the symbol M, meaning that this refers to any corresponding 16-bit memory location stored in the HL register pair. Okay, so now the CMP command actually stands for compare the data byte in the accumulator with the data byte present in either the specified register or in the corresponding memory location which is stored in the HL register pair. Okay, so now since this is basically a compare instruction, so three conditions can arise. Now let's just take the example of CPI instruction first. So three conditions can arise. So first, the data byte in the accumulator is greater than the specified 8-bit data, either both are equal, or the data byte in accumulator is less than the specified 8-bit data. Now depending upon each of these conditions, the carry and the 0 flags are set. The carry and the 0 flags are basically set or reset depending upon these three conditions. Okay, so if I might just make a column over here, so whenever the data byte in the accumulator is greater than the 8-bit specified 8-bit data acting as the operand, then in that case both the carry and the 0 flags are just reset. Okay, so they're just kept at the logic 0 levels. Now if both of them are just equal. I mean, if the data byte accumulator and the specified 8-bit data as the operand are both equal, then in that case the 0 flag is set to logic 1 level while the carry flag gets reset. Okay, and in the third condition, well, the carry flag is set while the 0 flag is reset. Now you can see that, well, arranging this way we are getting a sort of a sequence. Okay, so 0 1 2 something like that. It's a binary sequence. So this way, if you just keep this particular table in mind, then it'll be quite easy to work with these instructions. Now similar is the case for the CMP instruction. The operand is actually a register or a memory location loaded in the HL register pair. So this also just turns out to be setting the carry and the 0 flags in pretty much the same way, depending upon whether the accumulator data is either less, greater, or equal to the data byte in the specified register or the memory location. So let's just highlight this with an example. Let's just start with the CPI instruction here. So if we have, let's say, well, an 8-bit data of A0H, okay, and let's say the accumulator will contain a data byte of FFH. Fine. So in that case, if we would write over here, this instruction that was CPI A0H. Okay, now in this case what will happen is that since the data byte in the accumulator, which is FFH, okay, is greater than that of this data byte, that is A0H, that has been supplied externally, then in that case both the carry and the 0 flags would just be remaining at their reset levels, or in the logic 0 levels, okay, since the accumulator data is greater than the specified 8-bit data. Now on the other hand, if we would have thought about taking some different data byte, okay, let's say the accumulator data contains FFH, not a problem, but if we would have, now this is probably the largest 8-bit data that can possibly be existing, okay, in the hexadecimal system. So if we take the external data, okay, to be FFH also, then in that case, by comparing them, if we would have written over here, sorry, that's just a mistake, don't mind. So if we would have written over here, we need to modify this instruction once again. So if we would have written here CPI FFH, okay, then in that case we would have got an equal to result over here, since both the data byte in the accumulator and the one supplied externally are just equal to each other. Then in that case the carry flag would have been reset and the 0 flag would have been set. Now if we make certain provisions to check the condition of the carry and the 0 flag bits, okay, if we make such provisions in our program, then by comparing them and just checking the condition of the carry and the 0 flags, we can basically determine the state of the result of this particular compare instructions. Okay, now the CMP instruction, well, it just performs in the very same way as you all know, but in this case only the way in which this is declared is a little different. Okay, so now if we have, let's say the register B what contains this data byte A0H and the accumulator contains the data byte FFH, then in that case, like the previous example, we couldn't have just supplied this data A0H directly, but we would have had to store it in some general purpose register if we were working with the registers over here, if that was the operand in this case. So in that case we would have written the instruction as well CMP B, okay, and if this data byte A0H would have been present in some memory location, let's say if it would have been present in some memory location, let's say 2050H, okay, where the data byte that is present is basically A0H, and now if we would have loaded the HL register pair with this data byte, with this memory location actually, that is 2050H, and now we could have referred to this particular 16-bit data in the HL register pair as M, since it points to a memory location. It is actually a valid memory location. Okay, so in that case, if this were the case and it contained the data byte A0H, then we could have written the instruction this way: CMP M. Okay, and it would have done the same thing or generated the same result as that for CMPB, as well as whatever we got for CPI, writing here A0H. So if this is the condition, then we know that the accumulator data is greater than the data A0H if it is contained in the register B. Then in that case, we would have both the carry and the zero flag set to the logic 0 levels. And even in the CMPM, okay, even in this case, the particular data in the 2050 memory location, okay, that is contained in the HL register pair is A0H also. In that case also, we shall see that the same thing happen, okay, since the accumulator data is greater than the data in the memory location. So again, the carry and the zero flags would just be reset. Okay, so this is pretty much of what happens in the compare instructions. And in the same way, if we just check for the carry and the zero flag bits status, then we can make a solid program to generate a suitable result using the compare instructions. Okay, so that said, we just would like to wind up our discussion right here, and we're going to see you in the next tutorial. And oh, I just forgot almost. Let me just tell you that the CPI instruction is a 2-byte instruction, okay, while the CMP is just a single byte instruction. And over here, it should be kept in mind that other than the 0 and the carry flags, all the rest of the flag bits are also affected. Now this just depends upon which of these 3 results are actually being generated, and also the type of data you're using. Okay, so that is just I mean, the effect on the flag bits is just specific for the particular result being generated, okay, in a particular type of operation that might occur in your program. Okay, so that said, we just wrap up our discussion right here and see you in the forthcoming tutorial. So till then, keep watching, and bye bye for now.